Welcome to AP Chemistry at Hononegah High School. Today we'll be looking at section 16.6, which is our third part of notes over chapter 16. And today we'll be looking at weak acids and weak acid equilibrium. So we're back to icebox. So today we'll be looking at ice or ice tables again. Now, for generalized acid dissociation, so looking at the general equation for how weak acids dissociate. And this is actually a shortcut you can use in pretty much any problem to see what's happening with acids. With bases, it's a little bit trickier sometimes, and you've got a little bit goofier things you're writing. Pretty much all acid dissociation is pretty much going to be the same thing. So you have some acid, HA, substance that donates a proton. That's going to be donating that proton to water, and you're going to get A- and H3O+. So this is our generalized reaction for any acid dissociation. Now, another way to write this, which is a little bit shorter but fundamentally the same thing, would be to say HA dissociates into A- and H+. Fundamentally the exact same idea between the two. And they're really used interchangeable. So down here for the Kc expression, you could also write this as the concentration of H+ times the concentration of A- over HA. So this is a generalized formula for pretty much any weak acid dissociation. One of the things you will do every single time is look at what the acid reaction is and write the Kc expression. And since we're talking about acids, we can interchange the concept of Kc with Ka. So typically what we're going to do from here on out is we'll call this Ka. It is really important in every single problem that you do, especially once we throw Kb in as well, that you recognize, is this an acid reaction or is this a base reaction? And you know that by looking for that. If you see H+ or H3O+ as a product, you know you're going to be talking about an acid reaction, and you know that you need the Ka for that reaction. So watch out for any problem where they give you an acid reaction, you see H+ or H3O+ on the product side, but they give you a Kb. That means extra work. So watch out for those types of situations. So everything we look at today is going to involve this general reaction for an acid. Now, one thing that's fundamentally true, and this is a truth that is important, so this is a truth you should know, is that the greater the value of Ka, the stronger the acid. So this is one of the fundamental ideas, and this frequently pops up in one way, shape, or form on the AP test. And there's probably a 100% chance I'm going to have a test question related to this. So you need to understand, the higher the value of Ka, the stronger the acid is. So when you look at this list of Kas here for these different substances, this one here, 6.8 times 10 to the -4th, this would be the strongest acid in this particular list. So what we're looking at here is a group of different types of acids, and notice sometimes we've got organic compounds like benzoic acid that has that carboxyl group. So does acetic. Other situations we're looking at the hydrogen stuck to like a cyanide, Cn-, or other types of things. But in every case, we have a hydrogen that's ionizable here, and it's only partially ionizable. And remember, the greater the value of Ka, the stronger the acid is, the greater the degree of ionization. Now, doing Ka problems. First type of problem you need to be able to do is calculate the Ka if you're given a pH for some sort of equilibrium reaction. And this is actually going to be similar to equilibrium problems we did last chapter. So one of the first types of mathematical calculations that you need to be able to handle with acid chemistry, weak acid chemistry, would be calculating the Ka if you have a pH. Now, one thing to keep in mind when we're setting up these ice boxes, you're quite often going to end up with, on the reactant side, a -x situation, so some value -x. Well, that pretty much throws us into the quadratic for most of the problems, if we have that. So a lot of acid-base chemistry is really quadratic chemistry. The nice thing is there are some situations where you can end up ignoring that x because it's going to end up so small that we can really neglect it. That's one of the things we'll end up looking at in the problems today. So while technically pretty much every problem is a quadratic situation, we can usually get around that. And one thing to keep in mind, the quadratic equation has not appeared on the modern AP test ever. So don't expect to see the quadratics there. But you do need to note when you're actually using 5% rule or another situation that I'm going to be talking about in class to ignore this. So I'm going to give you a couple of different tools to get away from the quadratic if we can get away from it. But pretty much every single time on the AP test, you'll be able to ignore the x, and that's something we'll end up looking at. So what we really do is, the book calls this the 5% rule, and that's how most books look at it. Like I said, there is another way I'll end up talking about in class, but for notes here, we're going to be looking at when the percent ionization is less than 5%, we can assume that the negative x value is so incredibly small that it's 0. And we can drop that from our icebox equation. We can drop that from the Kc expression with the x substituted in, and we end up with a very, very simple mathematical solution rather than the quadratic equation. And pretty much every case on the AP test, you'll be able to do this. And in many of the cases on the problems that you do in homework and for AP chemistry, you'll be able to use the 5% rule. So 5% rule is going to become your friend. So when you have it, it makes things significantly easier. And what it really does is it simplifies the math and avoids the quadratic equation. And since the quadratic typically doesn't appear on the AP test, what I'm going to end up showing you is something you can pretty much use every single time on the AP test. So here's a typical problem. The pH of 0.10 molar solution of formic acid, which is HCOOH. Remember, I've talked about this a couple times now. Recognize that as the carboxyl group, which has an ionizable hydrogen within it. So we are talking about a weak acid situation here. At 25 degrees Celsius for this reaction, the pH would be 2.38. So from that, we're going to calculate the Ka from formic acid at that temperature. Now, we always start with our equation. And by always, I mean always. Every single time you need to look at what's happening with the equation. And sometimes you can write it as the generalized form. In fact, with acid equations, we can almost get away with writing it just as that generalized equation. HA plus H2O makes A minus and H3O plus. That general form is something you can use in pretty much every case. You just substitute in the acid and its anion into the overall equation. So writing the general equation is just as good as typically writing this equation. Now, for this particular reaction, since it's an equilibrium reaction, remember we know that because it has the double arrow, we can set up a Ka expression, which would be the H3O plus times the A minus value, which in this case is HCOO minus, over the weak acid we're looking at, which would be HCOOH. Start every problem with that equation and writing the Ka expression. Now, to calculate the Ka, we need to know the equilibrium concentrations of all three things, because in every case, once we got rid of the water, because that was a liquid, so we're always going to ignore the water here, we're left with three species that we have to account for in the equilibrium constant. So we can find the H3O plus, which is going to be the same thing as the HCOO minus from the pH. Remember, the pH gives us our H plus or H3O minus concentration. And remember, based upon the Ka expression from the previous page, those two concentrations are going to equal each other. So if we take the H3O plus concentration, take the negative log of that, we get pH. So in this particular case, we were told the pH was 2.38. So what we really want to do is take e to the negative 2.38. I'm sorry, that's natural log. We're going to take 10 to the negative 2.38. So above your log key, we want the 10 to the x key. And don't forget, it's got to be negative 2.38. Otherwise, you're going to get a really large number, which we don't want, rather than a really small number. So don't forget to make it negative. So above the log key on your calculator is the 10 to the x key. So you're going to get that key, and then you're going to put in negative 2.38. And that will return our value for our H3O plus, which remember was the exact same. They were equal. It was a 1-to-1 stoichiometry. These two concentrations had to equal each other. Now, one thing I'm going to review here, looked at this a couple of times in last night's homework. When you have a pH with 2 decimal places, that means 2 sig figs. So don't forget that idea. In fact, one of the first things I'll often do in problems when we look at the very beginning is, oh, notice they give us a pH to 2 decimal places. That means 2 sig figs from here on out. So we end up with 4.2 times 10 to the negative 3 molar would be our concentration of our acid, and or I should say our hydronium, as well as the anion of the acid, its conjugate. So when we take a look at what's happening in our ice table, remember they said we had a concentration of the acid of 0.10 molar. And at time 0, we have initial situation here. We have absolutely no H3O plus and HCOO minus. From there, then, we're definitely going down on reactants and up in products. It's a 1-to-1-to-1 stoichiometry. And we knew that the substance was going to be going down by what these two were going up. So remember, this was really a positive X situation. This was a positive X situation. And we established that value of X from the pH. So the pH gave us that. Well, if we know this, and we know this is equal to it, and we know that has to be the negative of it. So all of that really fell from our pH value. So keep in mind, when you go to do these problems like this, where they give you a pH, and they're asking you to find the Ka, every single time, this value is going to come from the pH. So you establish that from pH because that's what it represents. pH is the negative log of the H3O plus. So 10 to the negative pH would give us our H3O plus concentration. And then you establish your other two from that based on the stoichiometry. So the last thing we can do is solve these things. So add I plus C to get E. And in this situation, we end up with 4.2 times 10 to the negative 3 for both of our concentrations of products, and 0.0958 for the concentration of our acid. Now keep in mind, when we're subtracting these two things, literally it's 0.10, and that's going to be minus 4.2 times 10 to the negative 3. It's easier to see what's happening here if we put it in regular notation. So that's going to be decimal point, 2 zeros, and a 4.2. Notice what happens here with rounding. I know we're going to subtract this, but this needs to be my last significant digit. So my last two digits here are going to round out. Since the next digit past the 9 is a 5, we end up with 0.10. So for all intents and purposes, yes, our concentration did go down, but we had such a large value for our initial concentration that when we subtracted out how much went down, for all intents and purposes, it went down 0 by sig figs. So that's why when we get into some certain situations, we can end up ignoring a value, which helps us avoid the quadratic later on. And remember here, to 2 decimal places, the HCOOH at equilibrium is 0.10 molar. And remember, that's often going to happen if our dissociation is small compared to our initial concentration. That's really the key, is how much is it dissociating compared to what we have. And that's really where this 5% rule comes in. If you're less than 5% dissociation, you can end up ignoring how much you go down. Now that I've got my 3 concentrations, I can plug those into the Ka expression and solve for Ka. So in this particular case, 1.8 times 10 to the negative 4th. Remember, 2 sig figs, because we started with 2 decimal places in our pH value. So that would be a typical problem where you're solving Ka if you're given the pH. Pretty much every single time they give you the pH, you're going to have that form of the icebox where you know what your C's are so you can find your E's and plug in. You're never going to be dealing with X's when they tell you the Ka. Now, the whole idea of percent ionization. So before we get into situations where we might be able to use the 5% rule, I want you to understand better what we really mean by percent ionization. Remember, every percent, always, forever, always in life. Percent is always part, if I could spell, over whole times 100. So percent ionization would be no different. On top, we're looking at the part that ionized. Remember, that would be at equilibrium, our H3O plus concentration, because that all came from our original weak acid. And then the whole would be what we started off with for our initial value for that weak acid. If we divide those two and multiply by 100, we get percent ionization. So in the example we just looked at, remember H3O plus was 4.2 times 10 to the negative 3rd. Our initial concentration of the formic acid was 0.10 molar. So when we divide and multiply to 2 sig figs, we get 4.2%. Now remember, we ended up subtracting out a number that was so small it didn't make a difference in our initial concentration. And notice that was 4.2%. That's less than 5%. That's actually where this 5% rule comes in. Well, how it works out is that every single time your percent ionization is less than 5%, based on sig fig math, when you do your subtraction, it'll end up rounding out. So therefore, you can ignore it. And you can ignore it every single time that happens. So whenever your percent ionization is less than 5%, it ends up being able to be ignored. And we're going to end up using that. So the basic idea here was acid equilibrium at equilibrium minus X equaled the same thing as the acid equilibrium in rounding. That's always going to happen when the percent ionization is less than 5. So whenever you have a situation where they don't give you the pKa, or I'm sorry, where they don't give you the Ka, you're going to end up with this on the bottom of our Ka expression. And what you can say every single time that it dissociates less than 5% is you can do exactly what I'm going to do here. You're going to cross it out with a line here, and underneath it you're going to write neglect X. Every single time do that. And that allows you then to validly neglect it on the AP test and not have to do the quadratic. So while there are some problems where people end up using the quadratic on the AP test, there's never a problem where you really have to. And that's always going to come up here with really this acid-base equilibrium type situations. So that's in the next problem we're going to see that that can really dramatically simplify the math. So we're going to look at that 5% rule in application, and we're going to use that neglect X thing whenever possible. So here's a typical pH problem from Ka. So in this particular problem, it says calculate the pH of a 0.30 molar solution of acetic acid, and they give us the formula for acetic acid from which I can write the general acid reaction. Remember, you need to be able to take this and write this every single time. That's the starting point for every problem. Sometimes it's given, sometimes it's not. You need to be able to do it. And then from there we can write the Ka expression. And remember, in this particular problem, right here they give us the Ka. Hint, every time you see they're giving you the Ka, you're going to do solve for X. So you're going to end up with X's at equilibrium. Something we did last chapter, you're going to see it a lot this chapter. But we'll see a lot of time it simplifies. So for the Ka for this particular reaction is 1.8 times 10 to the -5. Every time you see the Ka value, you're going to end up with X's in the E spot in our icebox table. Okay, so the equilibrium expression in this particular case, H3O plus times our anion, so H3O plus times A minus over HA, just like it always is with acids. Next, we set up our icebox table. Now, we knew initially we had that acid, and we know initially we have 0 dissociation, so we're going to have 0 amounts here, and from there we're going to go down by X. And since we're going down by X on the reactant side based on the stoichiometry here, we're going to go up by X on each of our products. So when we add them together to get our equilibrium expression, our two products are going to equal X, and our reactant is going to equal 0.30 minus X. Now, one of the things I've said is it's really nice if we can ignore that X, so we can neglect X. That would be really, really convenient whenever that happens. Well, in this particular case, what we're going to do is we're going to assume that X is really small and we can ignore it. So that's how you do one of these. You assume that it's really small, and then at the end we double check to see if that's valid, and if it was valid, we're good and we move on. So in every single case, we're going to be doing this in neglect X thing. But before we move on, we double check to make sure it was a valid assumption. So what we're going to do is assume that at equilibrium, our concentration is the same as it was initially. Is it a valid assumption? Well, that's what we'll end up checking eventually. So we will check that out. So what we do is we now have this form of the equation, which since it's not 0.30 minus X on the bottom, we don't get the quadratic equation. So it's very, very easy to solve. You're going to get used to this general form a lot. X squared over the initial concentration is going to equal to K. You do that pretty much every single problem. You're going to set it up that way. Now in this particular case, X ends up solving for as 2.3 times 10 to the -3rd by simple algebra. Now, was this a valid assumption? Well, the real question here is this less than 5% dissociation? Remember, we started with 0.30, and what we're saying is it disassociates this much, to 2.3 times 10 to the -3rd. So we take our equation that we looked at a second ago. On top, we put what our concentration is of our acid. our H3O plus, I should say, not our acid. And on the bottom, we're going to put what our original concentration was. We divide, multiply by 100, we get 0.77. Yes, this was a valid assumption. So by 5% rule, this is less than 5%. So at this point, we are done. And we know our equilibrium concentrations are going to be 2.3 times 10 to the negative third for our X, which, remember, both things were the same. So our H3O plus, so our hydronium ion, as well as our A minus, the anion, the conjugate of our acid, both of those are going to be that value. And we don't have to do any extra math. We can avoid the quadratic. So at this point, we can take, to get our pH, plug in that value. Remember, the negative log of the H3O plus is the pH. And since we had 2 sig figs, we get 2 decimal places. Remember that. That's how we do the rounding with these. So the final answer ends up 2.64. So if they're giving the Ka value, you're going to do an icebox problem to determine your H3O plus concentration and then use that to get your pH. Now, let's look at a second problem. Hint as a warning, this is going to be a greater than 5% situation. So this is one where we can't neglect X, but we're still going to try and do it anyway. So calculate the H3O plus concentration and pH in a 0.100 molar solution of nitrous acid, for which the Ka equals 4.5 times 10 to the negative fourth. Now, first off, nitrous. Well, nitrous, that comes from nitrite, so that's NO2. And since that's a -1, we need 1H. So what we're dealing with is HNO2. Disassociating when we throw it in water. So that's the reaction you need to be able to write here. Remember, if it's not given, you have to be able to write this. And then you have to be able to determine your Ka expression. These 2 steps you're going to do basically every single problem. So I now have an expression. And now I'm going to set up my icebox problem. My initial concentration of my acid was 0.100. I have 0 of my reactants at time 0. So as this reaction proceeds, that's going to go down by X, and those are going to go up by X. Now, what we're going to end up doing here is add those together to get that. Now, we are going to assume, because every time we assume this, we're always going to assume that this value of X is so small we can ignore it. So what we're always going to do is this neglect X thing. Remember, I want you to write this. When you do this on your table, I want you to write it on your homework when you do it. I want you to write it on your reviews. Use this every single time. You need to say for the AP test that you're neglecting the X. So get in the habit of doing that every single time. So that's got to be there. So what we're going to do is start with this information. So when we set this and plug these equilibrium amounts into our Ka expression, we're going to end up with an X squared over 0.100, and that equals Ka. Looks familiar because they all have this general form. And we neglected our X here. Remember, this is supposed to be minus X, but we said that we're going to ignore that. And that ends up simplifying our math here. So algebraically, it's very quick to get X. Now the question is, was this a valid assumption? Remember, 5% rule. We take our X value, that's how much it dissociated, and divide it by what it started out at, 0.1. In this case, it's greater than 6.7%. And what that fundamentally means is this is not accurate. It's going to be in the ballpark of what our actual X value is, and that would be what our H3O plus concentration is and our A minus concentration, our conjugate base of the weak acid. But it's not correct, and that's really what it comes down to. So if our percent is greater than 5%, then this was an invalid assumption. We can't neglect X. So that means you basically need to use the quadratic. Now, I will give you another alternative. So you just absolutely hate the quadratic. I'll show you another way you can do this. But you still have to go through and fundamentally do the same thing at the beginning. You need to go back to our original equation, but now we're saying we can't ignore that. Now, if you're going to use the quadratic equation, you would basically multiply this out and get it in its quadratic form. The other method is successive approximations. We'll look at that in a second. So, once we've got it in quadratic form, now we can, if you're using your graphing calculator, you can plug this into your quadratic solver. If you're not using a quadratic equation, you can plug them into the quadratic equation. So this is going to be our B value, and -1 is going to be our A value, and this is going to be our C value. We can plug that into the quadratic equation and solve. And when you plug it into that equation, in this particular case, you get these 2 values. Now, You're always going to get two values, and just like before, there's a value that you can end up ignoring. In this particular case, X is concentration. Does it make any sense that you would have a negative concentration? And the answer to that would be no. So what we're going to do is we're going to keep the 6.5 times 10 to the negative 3. So that's our solution. Remember before we had 6.7 times 10 to the negative 3? We are close, but definitely different. So this is slightly different than what the previous number was. Sometimes it's going to be even farther away than that. But like I said, our first one gives us a ballpark idea, but the quadratic actually gives us our actual value. So when it's greater than 5% dissociation, our neglect X is invalid, and you have to go to quadratic. Now, there is another alternative. Now, if you recall our first assumption, we said that the X was going to be so small it might as well be 0. So what we always do, and we got 6.7 times 10 to the negative 3. Now, there's a method called successive approximations. So we've made a guess here, and there's a way to narrow this down and get even closer. So this is a second technique. It's one that a lot of books don't show, but what we can really do here is we can use that for our second approximation. If we pretend this is X and actually plug it in where X was, we don't have to use the quadratic equation. And notice now when we solve for X, we get 6.5 times 10 to the negative third. So on our second approximation, we end up with our valid answer. So rather than doing the quadratic if you don't want to, you can always use method of successive approximation. Now if we get really large percent dissociations, you would have to keep doing this until you eventually got the same thing twice in a row. But for the types of acids that we're going to be dealing with, at your second assumption, you're going to get the right answer. So you can avoid the quadratic if you want using the method of successive approximations. So you could plug that back in and try again and see, but you're going to find at this point it won't change. So you're going to stop at your second one. And while, like I said, there are situations where that could happen, you're never going to see one where we're dealing with weak acids. So at this point, we now know that our H3O plus is 6.5 times 10 to the negative 3. Remember, it said what is the concentration and what is the pH. The last thing we need to do is take the negative log of it. And remember, 2 decimal places, or 2 sig figs, 2 decimal places. So 2.19 would be our answer for pH. Now, last thing I want to really look at here is when we have a polyprotic acid in this whole situation. So we've been looking at really monoprotic acids. Pulling off one hydrogen, every equation basically looks the same. You have HA reacting with water to make H plus and A minus, or H3O plus and A minus, depending on how you want to look at it. But if you have a polyprotic acid, then you have more than one hydrogen to worry about. More than one hydrogen is going to be going into solution, and that's going to end up potentially affecting your pH. So if you have something like H2SO3, yes, you can have a dissociation of one hydrogen, and you'd end up with HSO3 minus, and that has another hydrogen which can further dissociate into H plus and SO3 2 minus. So in this polyprotic acid, we have 2 protons that are going to come off. Both of these protons are going to basically contribute to the acidity of the solution. Now the question is, do they contribute enough to make a difference? So if you look, we have a Ka for this equilibrium reaction and a Ka for that equilibrium reaction. We can actually use what we just looked at a second ago to solve for the H plus concentration in each case, add them together, get our total H3O plus concentration, take the negative log of that, and we'd get our pH value. So we could actually calculate how much each one contributes and do 2 different math problems. But the reality is, you need to understand that it's always easier to remove the first proton. So you're always going to see a significantly higher Ka value for the first one. So that's going to contribute a much larger amount to the overall quantity. And remember that whole neglect X thing? If we weren't contributing enough, we could ignore it. Well, the same thing can happen here. So the first one always comes off at a much greater, with much greater ease than the second one comes off. So your Ka1 is always bigger than your Ka2, which is always bigger than your Ka3 if we had a triprotic situation or 3 hydrogens that could come off, like in phosphoric acid and a few other things. But what you need to understand here is, in terms of having to take into account that second ionization and the amount of hydronium that comes from that, well, we can pretty much ignore it if the difference in K from Ka1 to Ka2 is greater than 10 to the third. So if you're greater than 1,000, generally what the second value is. So in the case of ascorbic acid, our first K is 8.0 times 10 to the negative third. That disassociates, and that's going to contribute some H+, and that's going to cause a certain acidity. But this one is 10 to the 9 times smaller. It's a billion times smaller. I don't know what kind of significance you'd have to have in a problem to really make that warrant even calculating, but for all intents and purposes, that's more than 1,000 times smaller. It's not going to contribute any appreciable amount to the overall pH. So when you look at the different substances on this table, there's quite a few situations here where we can basically ignore what's given for that second substance, because while it does contribute, it contributes such a small amount that it's not valid. So even in a polyprotic situation, most of the time we only really have to look at the first K value. After that, it's a rare exception, like with something like citric acid or tartaric acid here, where we end up with the second ionization giving us enough hydrogen to worry about. And that ends our next set of notes over acid-base equilibrium.